as I was saying, these are the data from the EHP study on the California teachers. And what I'm going to talk about this afternoon is how do we know which pollutant is real and which are not, which is a very tough question, and not all studies even ask that question. So what I have done, first of all, you have to put all the pollutants on a common basis, which means you can't use 10 micrograms or 10 ppb. We've calculated the risk on the basis of the mean concentration. And what I've done here is plot the risk of the mean concentration against the pollutants correlation with OC. Now, someone a lot smarter than me once said that all epidemiology results are due to either chance, bias, or cause. It's got to be one of the three. So if we assume that OC is cause, then since all of these species have risks lower than they would have gotten just due to their correlation with OC, all of these are chance. Now, this is just one way to look at it. The hypothesis is that, for example, PM2.5, the hypothesis is that PM2.5 risk is coming solely because it's correlated with OC, which is the real bad guy. Now, you can accept this or not, but I don't know of another way to do it. I'm going to come back to that in a minute with respect to the veteran study, but let's go on now, please, and talk about what's correlated with what. These are, in this veteran study, which was published last year, we calculated concentrations. We had other people calculate concentrations for both these species and air toxics for every county in the U.S. And they're based on emissions and some very fancy dispersion modeling. It was not cheap, because I know, because I paid for it. And what we plotted here are the relationships among these five pollutants, against elemental carbon, which is a marker for diesel. What we find that SO2 and NOx are highly correlated with diesel. Not a big surprise. PM2.5 is not. Sulfate is not. Is even less so. So this set of three pollutants are highly correlated with one another. That's what we learned from this. Next slide, please. Now, if we go to air toxics, we have a lot more species to choose from. I think there's 180 in that set, and we only looked at 12 of them. And this information is available on the web from the National Air Toxic Assessment from EPA. And they again have values, concentrations for every county in the U.S. So this time we're plotting it against traffic density, which is the number of vehicle mile traveled per year per square mile in a county. It's county averages. What we find is that up here, nickel is highly correlated with traffic, diesel pretty much so, and POM is pretty much so. So these four are going to be difficult to separate. And if we look at some of the other toxics, benzene has a background levels. So perhaps that might be separable. Manganese goes very much with traffic. Arsenic does not. So I'm pointing out to you that there are 58 data points on each one of those plots, one for every county. So when you go to this kind of a database, you're not limited to EPA monitoring anymore. Now, one can argue, well, how accurate are they? We haven't really checked that. We find good correlations with measurements, but the point here, the important point is here, that whatever errors are in this database, they're pretty much the same on all the pollutants, if you believe the emissions, because they all come from the same model. Whereas when you look at measurements, you've got one set of problems with measuring PM2.5, you've got another one with measuring CO, they're in different locations at different times. This I highly recommend as a way of getting around that problem. One more, please. Now, this is from the Speciation Trends Network nationally across the country. Same kind of thing. Against elemental carbon, we find zinc is highly correlated. Zinc comes from tire dust. Say, hey, that relates. Silicon comes from road dust. That does not relate. PM2.5, not so much. Okay, next please. I'm going to skip the words. You can read those for yourself. And go to the next set of pictures, one more. Now we're looking at stuff from the Veterans Administration study that I just mentioned, published in April of 2009. And what we've done is look at all the species that we considered and and played some word games saying, all right, what if benzene is the true bad actor? What if that? This is for all subject mortality, all counties for which we have data. It's about 200 counties. And we find here that no pollutant for all subjects has a higher risk than benzene after you account for the correlation. So we will conclude from that, okay, it looks like benzene's the bad guy. Next, please. If we play another game and say, all right, no, I'm not sure. I think maybe NOx is the one that's more important. We find that these guys are sticking up above the curve, so that hypothesis is rejected. And where we are is that this group of pollutants here are all highly correlated. Look at the values of correlations. And these are subject-weighted correlations, which is very important. You have to go where the people live. And when you have more people in a big city, you get a higher correlation. If you just look at the raw data, you get something quite different. But if people don't live in those counties, it doesn't matter. Next, please. Now, we also found in this study that whereas the risk for all subjects are up to 0.1, if we divide the data set in half according to traffic density and take the highest traffic density locations, we get risks up to 0.2. That says all the risk is coming from the high traffic locations. Lo and behold, we found a threshold. Now, we didn't find it very accurately, but we showed that it's not the same everywhere. And what we have here is that the story's a little bit different. NOx and EC are sticking out against benzene. PM2.5 is not on this slide because we can't calculate PM2.5. It has too much water in it. But here's diesel. Diesel is no worse than anything else on this slide. Next, please. And if we then do it again and plot it against NOx, we find benzene and formaldehyde are high, diesel, SO2, nickel are not particularly. So I'm just pointing this out to you is that there are ways to get around the limitations of ambient air quality data. And finally, and we found some thresholds. Next, please. These are two pollutant models where the second pollutant, this traffic against a bunch of other things one at a time. And you can see that benzene, formaldehyde, diesel, and NOx over here, all with high risks. Combined, the traffic itself is not doing much. But when we come to SO2 and SO4, traffic is more important. So there are things you can do with two pollutant models. Let's go on. Next, after that. Now, statistical significance is often used as an arbiter in epidemiological studies. You will read, we tested the hypothesis that PM2.5 was related to XYZ and is statistically significant, so therefore it is. However, what you find when you look at a whole range of pollutants is that some are more variable than others. And in any epidemiological study, you have to have variability in the pollutant. This is the last one. A pollutant that's constant is not going to show a risk for anything, regardless of how toxic it is. So what we find is that there's an enormous range in variation. We found statistically significant effects of polypropylene and chloride at about 1%. But the reason we found them is because they're so highly variable. The risks for benzene, formaldehyde, and diesel, etc., are 10 and 20%. So statistical significance is a necessary but not sufficient consideration. I think that's all I have time for. One more thing. Next slide. We saw that one. Next, please. Next one, please. Some correlations for 3,000 counties without subject weighting. And I just want to point out SO2 against diesel PM 0.7. That's pretty high. SO2 against traffic density 0.4. And if we look at the average correlation to see what pollutants are highly intercorrelated with each other, we find benzene, diesel PM, and formaldehyde are pretty much correlated with a lot of stuff. Things like nickel are not. So I would just try to advocate for the fact that we need to look at a lot of pollutants and not just the one that happens to be the one of interest. Thanks very much.
Okay, thank you, Fred.